During this series of videos, we will go through some of the fundamentals of FEBIT, but if you want to go in greater detail, I strongly recommend you this review article written by Ivo Utke, Patrick Hoffman, and John Melingalis, where many aspects of FEBIT are described. FEBIT is a very complex process. When the gas molecules are delivered by the gas injector system, they will get adsorbed and desorbed with a given rate. They will get dissociated and the volatile fragments will be gone, but they can also interact with the focused electron beam in between. And we also have the diffusion of the molecules in the substrate, as well as with the geometry that we are creating, which can be particularly complex if it is 3D. These are competing processes, and many of them take place at different length scales. And in fact, FEBIT, as you can see, can be considered a technique that involves processes that go from the femtosecond regime to hundreds or even thousands of seconds. The important message here is that when we are depositing in 3D, we are typically using times of deposition that are characterized by dwells that are typically in the millisecond to 10 of millisecond regime. And these are normally larger than the characteristic times that are important for all the processes that I just described. It is also important to mention that the interaction of electrons with matter in a solid or gas phase is very complicated, and you can imagine how the primary electron, when it interacts with the substrate, it will have a lot of scattering events, generating a series of particles. It can generate backscatter electrons that have high energy than the secondary electrons that typically have energies below 50 electron volts, and the scattering cross-section, in other words, the probability of these electrons breaking the bonds of the molecules that we use in FEBIT is higher for the secondary electrons than for backscatter or the primary electron beam. So that means that when we are incident with a primary beam of electrons, the main responsible for the position will be the secondary electron, the low energy electrons. And when one of these reaches the surface and there's a molecule here, there will be a higher probability that the decomposition takes place. You can see, for instance, for the case of tungsten hexacarbonyl here, how the deposition cross-section peaks around a few hundreds of electron volts, but not for the kilo electron volt energy that we would be using in the primary electron beam. So many important parameters of the FEBIT deposit depend on many of these parameters. So the 3D geometry, the material composition, the electrical, mechanical, and thermal properties, etc., critically depend on parameters that, of course, we cannot control. What we can control as a user is the current of electrons, the voltage of to which the electrons are accelerated, the dwell times, the time the beam is in a given spot, the overlapping between neighboring points, the base and growth pressure, the pattern strategy, the GIS geometry, the gas flux, etc., etc. So, of course, this makes everything really complicated because there are many parameters that I can control. And in f3ast, what we have done is to synthesize the essence of the FEBIT process in order to find the key parameters that are required to be able to do a 3D printing process. In order to tackle the complexity of FEBIT, there has been a lot of development in the last years by the FEBIT community, creating different types of computational tools. I would like first to mention the FEBIT continuum models. These are partial differential equations that describe what is the evolution over time of the adsorb rate depending on the gas flux, the electron flux, etc., etc. We will talk about it later in a different video. And the FEBIT continuum models gives us really key information about the FEBIT process. Starting, for instance, for the vertical growth rate, how fast the deposit grows as a function of the different competing interactions that we have, or, for instance, the shape that I have during the deposit, which may depend on many parameters, in this case, as a function of the dwell time. We have extended the Febit continuum models, creating the Febit frequency maps, which is a way to show what type of growth regimes we may have in Febit during deposition. We have done this for a single adsorbate, Langmuir adsorption, and also for a multi-adsorbate case. And not getting into a lot of details, but basically in this axis we have the renormalized characteristic Febit frequencies. You can see that there are different regimes here separated by these lines. When we want to do 3D printing, we want to be typically in the reaction rate limited regime. What this means is that we are limited by the amount of electrons that we have in the system. So we will have a lot of gas, and then when the electrons come, they will deposit where the beam has been placed. This is an ideal scenario for 3D printing. The completely opposite could be to be in the mass transport limited regime, where we would be limited by the amount of gas that we have in the system. So we would have a lot of electrons, and then when a gas molecule came, it could be deposited. But of course, we don't have such a control over the distribution of gas in this case. So therefore, this is not a good scenario for 3D printing. What we will also show in other videos is that we typically are in a slightly different regime, which is a variation of the reaction rate limited, which is called the desorption dominated. In this case, we are also limited by the amount of electrons that we have in the system, so that is good, but we also have a strong desorption due to temperature effects. The materials that are deposited typically have a low thermal conductivity, and this brings as a consequence that we have some heating and the molecules get desorbed quickly. So this is the regime that we will typically have in many cases during a Febit 3D printing process. For completeness, I would like to also show you other computational tools that the Febit community has been developing. For example, this gas injector system that calculates what is the gas flux distribution in the substrate depending on the dimensions and geometry that we have of the gas injector system. This is very important when you design your GIS, your gas injector system. And it is also important to understand what type of gas flux distribution we are going to have, in particular if diffusion is something important. Another important Monte Carlo simulation, apart from the gas injector system one, is the electron-matter interaction. So here, what these tools do is they calculate in a probabilistic way the type of trajectories that the electrons will follow and the generation, for instance, of secondary electrons that are, as we described before, important for Febit when the electrons come in a given geometry at a given energy. And you can see the type of interaction that is created. This is typically called a pear-shaped interaction. And also, it's important to mention that these tools are now possible in some cases in 3D geometries, which is key for the type of 3D printing methods that we want to do. However, we will not, in f3ast, we are not using this type of methods because we take an effective way to take into account these effects, which are very important. Finally, there is also another type of tools that have been developed that focus more on the electronic molecular level. So when gas molecules, for instance, get adsorbed in particular substrates with particular radicals, what type of chemical bonds are created and what type of interaction these are created, the type of configuration that these molecules take during the adsorption, giving, for instance, as a result, autocatalytic effects, which are very important if I want to have a highly metallic material at the end, etc. So this has been done on the density functional theory level and also on the molecular dynamic level. Again, this is something that we are not using in f3ast. In f3ast, the only thing that we are using is the Febit continuum model, as I will show you later.